everyone, I'm Max from Harmony and we're going to talk about composability and CrossShard transactions today. So we'll start with the generic definition of composability. Composability refers to the ability of different systems to interact with each other. Now, to give you an example, think of this like Lego blocks. Two Lego blocks fit into each other perfectly and you're able to use the combined piece much easier. In the crypto space, this would mean the ability for, say, a random smart contract to access Uniswap for exploiting some arbitrage opportunity, or just the ability for a DAO to manage its treasury by investing it in Yearn. Now, composability is different from interoperability. I would say it's a superset of interoperability. For example, your bank and your PayPal account, or your credit card and your PayPal account, are interoperable. They can talk to each other, but that's where the relationship ends. The bank cannot access PayPal's data and PayPal cannot access the bank's data. But composability goes a step further. It makes it entirely permissionless. Any random smart contract is able to access another random smart contract's information without checking for permission. Now, there are three types of composability. Very basic definitions. First is the morphological composability, which just means that things are made in such a manner that they follow the same overall standards. So, for example, the ERC20 standard is fairly common. Everybody understands it. You can access any, you can take any generic ERC20 and it will have similar functions as another generic ERC20. Next is the syntactic composability, which means which is like a step forward from morphological composability. This means one contract can access another contract's known public methods. So think of Uniswap. Uniswap is built in such a manner that it can access any ERC20 entirely, and it's fairly easy to create a new pool of Uniswap liquidity pairs. That means Uniswap and ERC20s have syntactic composability. Now the last one, which is the, let me just write this down. Now the last one, which is atomic composability. This is a big one. In effect, atomic composability means the ability for a transaction to occur in such a manner that you're able to say either I want it all or I want none. So think of this as a very simple example of a flash loan. As an end user, you're able to borrow from a liquidity pool. When you borrow from a liquidity pool and you execute a transaction based on that borrowing, you're supposed to return your funds, return the borrowed funds within the same transaction. If at any point in time any of this fails, the transaction does not go through. This means this flash loan is atomic. There is no way for a secure flash loan to work in such a manner that somebody borrows funds and does not return them. This is what atomicity means. And atomic composability is obviously composability on top of atomicity. So now a caveat of atomic composability is that it will only happen if everything is on the same execution layer. This means that if you're trying to initiate or trying to perform an atomic transaction, it will only happen if, let's say, the entirety of the transaction is on Ethereum. You cannot make a flash loan that starts on Ethereum and ends on Polygon, or goes to Polygon and then comes back. This is not possible because it has to happen within the same transaction. In effect, it has to happen within the same block. Now, just a sidebar here that in the non-crypto, the Web 2 world, composability has been on the decline because a lot of major companies end up creating walled gardens after attracting enough users. So for example, Google Talk when it originally existed, and WhatsApp, which still continues this day, they were based on open messaging standards. These messaging standards still continue to exist. There are apps based on these messaging standards, but Google Talk and WhatsApp are no longer compatible with them. So in effect, what these companies have done is that once they acquire a certain amount of user base, they have closed off their gardens, and open standards cannot participate. So they are no longer composable. Now, in the context of composability on Harmony, so as you all know, Harmony is a sharded blockchain. It's EVM based. So within the same execution layer, which is within any shard, we have composability, same as that on any other blockchain. What we are here to talk about is the CrossShard composability. In terms of CrossShard, I'll give you an example of what a CrossShard transaction would entail. Right now, Harmony supports transactions that allow for the transfer of native WAN tokens from one shard to another. This is the current state. What we're working on is the ability for smart contract cross-shard transactions. So for example, if you have an ERC20, let's say you have USDT on shard 0 and you want to use it on shard 1 because there is a tap on shard 1 that you want to interact with. There is no way for you to do this right now. But with an upcoming cross-shard upgrade, this will be a possibility. Okay. Like I said, the execution layers and the account state and the storage model are all separate across the shards. Within the shards, there is not much communication between the cross-shard transfers that I mentioned, and except the validator-related communication. So all of our staking mechanism is handled by the beacon chain, which is shard 0, and as a result, it also handles the reward distribution for staking. And right now, most of the activity, well, almost all of the activity is on shard 0. So this leaves shard 0 validators at a certain monetary loss, because the shard 0 size is about 2 TB, more than 2 TB actually, but the shard 1, 2, 3 size is about 30 GB. So that's almost 100 times less. So in effect, shard 0 validators are economically penalized. There is also a minor difference in block times in shard 0 and shard 1, 2, 3. So there's another small penalty added to them. So what we're working on, we're trying to fix this. Hopefully, the load that gets distributed amongst shard 0 and shard 1, 2, 3 will help equalize this. Okay. And right. So how the cross-shard transactions are supposed to work? Cross-shard transactions in their current state may be implemented, may be used directly by an end user or by another smart contract. So the initiator, which is either a contract or EOA, needs to call a specified precompile. A precompile is a contract that exists on the node level rather than one that exists on the EVM level. So think of it this way: there are certain cryptographic operations that are way too costly to perform on the EVM just because of gas. Precompiles allow these operations to be offloaded to the node, where they can be processed for much cheaper, and the result is then sent back to the execution layer, which continues as it's supposed to. So we have created, well, we are in the process of launching this, but we have created a precompile for CrossShard messaging. how it works is that each CrossShard call needs to consist of the sender, the target shard, gas information, the nonce, and the payload. All of these are neatly packaged by ABI encoding and sent to the precompile at address 0xF9, still to be finalized, but this is the address we're going to be using for CrossShard smart contract calls. All of these package values, gas has a lot of information: gas price, gas budget, gas limit, and if there's any gas left over, who should it go to on the target shard. All of these 4 parameters, they're sent to this precompile, which validates them, make sure there's enough funds for the gas, and any value that is being sent as well. All of these are validated, and the message is then broadcasted to the receiving shard. Now, at the receiving shard, how do you make sure that the message actually originated from the sending shard, that it's a legit message, or whether it's a malicious message? Because in the crypto space, you can't really trust that the node operator is not running a modified binary. So this message is validated first, and then it is signed by the sending shard committee. So each message, therefore, is known to have been signed appropriately. On the receiving shard, the signing is checked, and then it's added to the transaction pool. If it's added to the transaction pool, so we have not created a separate CrossShard message pool, because we want CrossShard transactions and regular transactions to be a part of the same pool. We want them to compete for the same block space, because in effect they, there's no difference between normal transaction and a CrossShard transaction. So they end up in the same pool. In the same pool, we sort them by gas price to make sure validators receive the highest gas. They complete the transactions that have the highest gas first, and that's how the prioritization of transactions works. So each block producer will put this within the same pool as a transaction pool, and then once the block is made, it will be in the block body, where again stored as the same signature. So once a block is produced, we also want to be sure that the block is not malicious in any manner. So for a block to be validated by other validators, they also need to validate any transaction that's included in the block and any CrossShard message that's included in the block. So for them to validate the CrossShard message, they have to be able to validate its signing. So the entire signed message is part of the block, and once the block is broadcasted to any validators, they verify it in the same manner that I've described, and regular block production process continues. And okay, so how is a CrossShard message actually being executed? The parameters that are received on the receiving shard are the sending shard, the sending address, the gas price, gas budget, etc. have already been processed. And finally, we have the standard payload. So the payload is the 4-byte signature plus any data that goes with it. So it's ultimately going to be the same as a regular transaction. Only thing is, instead of it being signed by the original externally owned address, it's going to be signed by the sending shards committee. At this point, all of the transactions have been included in the block and the block has been proposed. If the block is proposed, it will get validated by all of the validators who can then commit it, and that's how our CrossShard transactions will work. Thanks. So what does two-block composability mean in the context of Harmony? Let's say you are an end user trying to transfer your tokens, ERC20 tokens, from shard0 to shard1. You execute a transaction that's processed on shard0. This transaction generates a cross-shard message which reaches shard1 and is included in the next block. This means within 2 blocks, your transaction and your cross-shard message are processed under the right gas values and conditions. And this means you have 2-block composability for any cross-shard transaction. Note that composability is different from atomicity because atomicity requires shard locking and a lot of shard interdependence that we don't want to introduce. There are some ways to introduce atomicity in on the smart contract level. For example, Vitalik proposed a mechanism where a smart contract on one shard could yank the state from its sibling smart contract on another shard. Once the state is yanked, it's able to do an atomic transaction on that shard and then potentially send the modified state back to the destination shard. But this is something that we're still exploring. But to give you another example of atomicity, let's say you build an ERC20 or an HRC20 with that spans multiple shards, and you want to keep the total supply atomic. So it would be possible for you to introduce a primary ERC20 destination and all of the other shards being secondary. This means on all the other shards, the only thing that you can do is a transfer. You cannot do mints and you cannot do burns. So this way you're able to control supply at one shard and ensure that any person who is trying to query the total supply always has the right value. Okay, thank you.